Now let's talk about graphing inverse functions. I'm going to start out with a relatively simple curve here. I'm not going to give a formula for it because I'm really more interested in thinking about this purely graphically now. And then I'll go back to the one we had a formula for, the 1 over 1 plus x, because it's a little more complicated curve. So if this is the graph of y equals f of x, okay, and it's got a few points on it that I'm going to use as anchors when we do the inversion process, like f of 1 equals 3, for example. Okay, and f of 0 is 1, f of minus 1 is 1/2. Okay, just for some simple points. I want to talk about the two steps that we talked about algebraically and talk about their algebraic analogs. Well, if y equals f of x, then in the algebraic example, we did first some work to say x is f inverse of y. And then we switch the letters. And I want to emphasize that in the algebraic setting, all the work seems to appear in the step where you do x equals f inverse of y, and then the kind of additional, kind of silly step a little bit is switching the letters. So the one that's it's a little less clear why that's so important. Here it's actually the opposite. This is a graph of both of these facts simultaneously. If you're going to say x equals f inverse of y, it specifies exactly the same pairs, x and y, that y equals f of x does, because they're the same statement, and you haven't switched the variables. So for example, saying f of 1 equals 3 is the same thing as saying f inverse of 3 is equal to 1. Okay? And if I don't switch the variables, I don't actually have to do anything to this graph, which is actually kind of good news. Like, actually, in some sense, you're already staring at the correct information for the inverse function. Okay, but that's not really what we mean by graphing an inverse function. I'm not just interested in taking this point 1 comma 3 and interpreting it in two different ways. One is that f of 1 equals 3, and the other is that f of inverse of 3 equals 1. Well, that's true. It says if I put input 1 into the function, I get output 3. And if I put output 3 into the function, I say, what's the mystery input? It's 1. And notice this does pass the horizontal line test, so that when I take that horizontal line over at y equals 3, there is only one x value that satisfies it. But what do we mean by graphing inverse functions? Remember, when we graph a function, to get an intuitive sense of what's going on, it's really important that the inputs are on the horizontal line. That's just a really important convention for our intuition and our understanding. So that's why switching the letters is actually quite crucial. Okay, so switching the letters to get y equals f inverse of x, that's crucial. But what's the analog of that in the graphical world? Well, switching the letters means switching the coordinates. If I have a point like here, this point 1 comma 3, switching the letters, the roles of input and output, is I have to switch that to 3 comma 1. Okay, because I want to create a new function where input 3 corresponds to output 1. That is a different point. Okay, so we can do that. We can do that point by point. Let's just do a few points, and then we're going to try to be smarter about it. So 1, 3 goes to 3, 1. Okay, 0, 1 goes to 1, 0. Minus 1, 1/2 goes to 1/2 comma minus 1 down here. Okay, and we can start to see that maybe if we started connecting those dots, we'd get something that would look like a graph. Well, let's do it, and then we'll think of a better way to do it in a minute. Okay, well, so it's really about switching the letters. That's the key thing with the graphical version, and the graphical analog of that is just switching xy to yx. Okay, but you know what? That doesn't sound very geometric to me. That doesn't sound like geometric language. Oh, switch xy to yx. What does that mean in terms of geometric kinds of transformations? Is it a rotation? Is it a reflection? Is it a slide? What is it? Well, what it is a reflection along this diagonal line. Okay, that's the line y equals x. Let's check that and see if that makes sense. Okay. Well, first of all, the things that won't switch, if we're lucky, this graph might go through that line. And something like of the form 5, 5, where y is already equal to x, if I switch that, it doesn't notice. Okay, that's a very strong suggestion that it might actually be a reflection on that line y equals x. Because if you ever think something's a reflection across some sort of axis, you better check, is a point on that axis going to move or not? And it's not going to move. Okay. Well, and then let's see. 1, 3 to 3, 1. Well, I didn't do a very good job of drawing it. Okay, but yeah, it flips across. 0, 1 to 1, 0. minus 1 to 1/2, yeah, it looks like they're flipping across that axis. And indeed, that's true. So here's the punchline that people usually often stop with. We just flip the graph across that y equals x line, the 45-degree line. Now here's the thing though. If you're really good visually at doing things like that, that might be good enough, and you just flip across the graph across the y equals x line. But people tend not to do that very well. I don't do that incredibly well. And here's what I actually recommend. I do recommend this as a final check. Okay, and what you can do is once you've got the graph of the forward function and the inverse function, tilt your head 45 degrees so you're looking up in the 45-degree way, and then it should look obvious at that point, fairly obvious, whether it looks symmetrical about that line. And it's important to tilt your head because humans are designed to detect left-right symmetry because we're designed that way, because our bodies are that way. And so that's really helpful. But it's not that great, this simple instruction to flip the graph across the y equals x line is not that great to create the new graph. Now, what strategy did I start out doing? And that's flipping points. That will work somewhat, but you don't want to just plot point after point after point and try to connect the dots in a kind of an okay way. That's not very efficient, and it often produces a pretty bad graph. If there's some special point, like an intercept, absolutely. If there's a point that is on the y equals x line, then plot that and note, hey, it's already plotted without switching. Now this one didn't have one, but in the other graph we will have one. Okay, but here's what I like to emphasize, is there's a qualitative dictionary here. Okay, here's what I would recommend for something like this. Okay, and it's not a purely graphical method, but it talks a lot about the meaning, and it also just really talks about interesting features of these graphs as well. Okay, if you're switching x and y, then any concept associated to x will switch to a concept associated with y. So for example, some part of the graph that is horizontal, or like a horizontal asymptote, will then become a vertical asymptote and vice versa. So for example, this graph looks like it has a horizontal asymptote approaching the x-axis as we go to the left. Okay, so that's going to flip to a vertical asymptote somewhere. Well, where? Okay, well, we'll see in a minute. Okay, other things, not like straight horizontal or straight vertical, but like a shallow angle, by which I mean something close to horizontal, like here, will switch to a steep angle. Okay. If I have the words left and right, if I'm going left on the original graph, that's going to be the x value gets more and more negative. That's going to go to the y value gets more and more negative. Oh, that's actually starting to say, oh, I think I know where that asymptote is going to be. Oh, okay. If I start here at this point, which I know reflects to this point, on the forward graph, I go left at a shallow angle towards a horizontal asymptote, which is the x-axis. The translation of that is the translation of left is going down, because this is x gets more negative, that's y get more negative. The translation of right is going up. But to go back to this one, instead of going left towards an x-asymptote, I go down at a steep angle towards a vertical asymptote that's at the y-axis. And so that looks good. And then again, if you tilt your head 45 degrees, oh yeah, that looks like it's symmetrical. But I think it's easier to create it accurately by saying, okay, I've got this thing is doing something and doing these features in the x column. Its inverse graph is going to do the corresponding features in the y column. What else? What am I trying to say? Quadrant. There we go. Not column. Quadrant 2 exchanges with quadrant 4. So like here, negative positive goes to positive negative, and vice versa. Quadrant 1 switches with itself, but of course it doesn't just sit there. The two halves of quadrant 1 flip, and the two halves of quadrant 3 exchange with each other. Okay, so that's the main part of the dictionary that really helps you. Okay, now what about the rest of it? Okay, here there's no asymptote after this. It just gets steeper and steeper. So this starts here, and I know that flips over to here. This goes up and to the right and gets steeper and steeper. So this goes to the right and up and gets shallower and shallower and shallower. Okay, so everything I do over here was based on this dictionary of starting at some point and saying, okay, what did the original graph do? And I'm going to do the flipped version of that for the inverse graph. So let's try this a somewhat similar example, but a little more complicated looking, with the y equals 1 over 1 plus x. Now, of course, because we have algebra, that was the f of x. The sort of cheating way would be, okay, this was 1 over x minus 1. Okay, but I'm going to totally ignore that, and you can use it to check my answer if you want by just graphing that. But what if we weren't able to do that algebra? I got this weird side lighting coming in, so I'm sorry if the brightness is oscillating wildly. Okay. It's just the time of day I'm doing this video. Okay, so this was the graph. This is a little more complicated graph of this guy. It's coming in, it goes through. Okay. Okay, so I'm just going to plot 1 point. That's all I'm going to do, I think. Well, maybe 2. Okay. That's the point 0, 1. Okay. That's on the original graph. Oh, you know what? Colors would be really good here, especially since these guys are going to cross each other. Okay. I'm going to go ahead and put in the line y equals x. That never hurts, even though I'm not going to just do this by pretending I'm really good at reflecting it across that. Anything that crosses, especially like these 2 places, that tends to really mess people up. Okay. So I'm just going to reflect that 1 point across to the point 1, 0. And then I'm just going to follow the directions. Okay, on the forward graph, going over here, for example, it goes down and to the right at an increasingly shallower and shallower angle and approaches a horizontal asymptote because it gets closer and closer to the x-axis. Okay, so that means this is going to go up and to the right. I'm sorry, it's going to go up and to the left. So let's do it. The right part means x increasing. That means it goes up. Okay. And the down part, down switches with left. So it's going to go up and left. This was getting a shallower angle and going to an x horizontal asymptote. This is going to get steeper vertical towards y. So like this. Okay. Oh, and you know what? I really should figure out where this crossing is. You know, that's worthwhile. Let's just do that real quick. I forgot to do that. 1 over 1 plus x, we want to know where 1 over 1 plus x, the y value is actually equal to x. So let's just do a little bit of algebra. Actually, you know what? That's not a good idea. Let's leave that to, let that be a mystery. It's a cool problem, but it's more than I want to do. That's why I didn't want to do it. It's going to cross somewhere, okay? Whatever that point is, if I've graphed it reasonably accurately, that shouldn't move. Okay, so this guy's coming down into a horizontal asymptote. That guy goes up into a vertical asymptote. Okay, and then you can always check it. Oh, okay, those parts of it look like they're symmetrical if I put my head in this direction. Okay, now this guy, if I'm going left and up, okay, that means down and right for the flip, okay, and it's approaching a vertical asymptote at x equals -1. Ooh, you know what? That means the pink guy is going to approach a horizontal asymptote at y equals -1. This guy was x equals -1. Anything in this column, an asymptote that has x equals, that's going to transfer to an asymptote that has y equals. Or in other words, the vertical asymptote became a horizontal asymptote. Okay. I don't want to suggest that this is like, oh, this is easy. Notice I'm doing it very careful step by step. Every single feature I'm analyzing with this chart, with this dictionary. And I don't necessarily know what's going to happen at the start. So I'm going from this point, and the corresponding point is over here. This guy's going left and up. So this guy's going to go down and right. And it's going to approach that asymptote. Okay. Now again, if you look at it, diagonally, you can convince yourself, yeah, the black and the pink are symmetric. Okay, now what about this guy? Okay, this guy starts, let's start at the intersection point. And we could try to figure out where that is, but it's actually kind of subtle. Okay, you're going to start out at that point, and let's see, let's flip this part first. This is going to that vertical asymptote x equals -1, and so that, you know what, this is a little confusing. That actually, I didn't graph that terribly well. Let me draw the pinks, the green in here. Okay. This should be crossing right where those guys cross. Okay. Okay. Okay, where Where's it going to go? I'm just trying to fiddle with my colors here. Okay, so the 1 over 1 plus x here is, let's see, let me just draw that a little more accurately. So that's coming in like this. Okay. Okay, so now that's going to flip. So like let's go over from here, okay? I've got this thing coming in from a horizontal asymptote on the x-axis, and that sun is going down real quick. That should help. Okay. This guy's coming in from a horizontal asymptote on the x-axis over here on the left. Okay, so that's going to be coming in from a vertical asymptote on the bottom. Okay. Pink. Okay, so this guy is going to flip over to here. Okay. Notice this is all in the third quadrant, so it's going to stay completely in the third quadrant. Okay, so this guy's going to come up from that vertical asymptote. And what does this guy do? This guy goes to a vertical asymptote x equals minus 1. Okay, well, what does that do? It goes to a horizontal asymptote of y equals minus 1. And so that's going to come up to here, like that. Okay, and of course they're going to cross at whatever that point is where it crossed y equals x. So again, look at it. I didn't do a great job on that one because I kind of squeezed it. But again, if you look at this guy, these guys match across the line, the pink and the black. Okay, so I purposely picked a fairly complicated example. If that's intimidating, I wanted to pick one that had a lot of the features that makes this process hard. Crossing the y equals x line multiple times, various kinds of asymptotes, but the main thing is this idea of start with some point that you know what it's doing, or start with some feature like an asymptote, and trace along and follow these rules and see how the pink curve, the inverse curve, is generated out of the black one, the forward function curve, by just flipping all of these words. Alright, and you can apply this to any kind of inverse function, exponentials, logarithms, trig functions, and in other videos I do just that.